guys. So we can pick up where we left off, sort of talking about these Grignard reactions. We did a problem going from our reactants to our products. Now we want to make sure that we can work backwards as well. Given a particular molecule, we want to be able to tell which two substrates we would use to create that in our Grignard reaction. And what these arrows mean is we could actually have two different options depending on which bond we're going to say is our new carbon-carbon bond. Both of these would be acceptable. There's not any sort of rules, kind of like how we had for our Williamson ether synthesis, where there's a preference for what's what. Here you could pick either one of them, and that would be fine. So I'm just going to arbitrarily say, let's make that one our new bond here, okay? And everybody take a second and give me my substrates that I would need in order to create this molecule, this secondary alcohol, using a Grignard reaction. All right, so first of all, we got to remember what reacts with Grignards, right? What functional group are we going to have to start with if we're going to be using a Grignard? What do Grignards react with? So that is the Grignard, so we're going to need something, the Grignard, one of them is going to have that MgBr, and what's the functional group of the other molecule going to have to be? An aldehyde or ketone, right? So those carbonyl carbons are what react with our Grignards. So I'm going to have an aldehyde or a ketone here. Right? One molecule is my Grignard. It's got that MgBr. The other one is my aldehyde or ketone. Okay. We kind of have these I'm going to be a little bit better about explicitly writing down what I think are like the step-by-step strategies here, because up until now I've kind of been saying a lot of them verbally, but I think then we fall into this trap of you following along and say, yes, I can see what he's doing there, excellent. And then you go to do it on your own and it's like, okay, wait, what? All right, a best piece of advice I ever got was from a math professor when I was very early starting off, and I think it applies for all sciences, which is when I'm walking through it, it's all logical. So following along is one thing. You're like, yes, okay. Doing it yourself is a completely different ballgame, all right? So let's make sure to be explicit about writing our steps in our notes. That way, if we get stuck, we can have this list of procedures that we can turn to and figure it out. So again, in these reactions here, step one, we got to know we need aldehyde or ketone with our Grignard. All right, step two, we got to identify our new carbon-carbon bond. And I explicitly pointed to one here, but let's just real quick identify new carbon bond. Okay, importantly, it's going to be, that new bond is going to have to be between the carbon at the base of that oxygen and one of the carbons on either side. Again, I could have picked either one of those there to be my new carbon-carbon bond, but I definitely know that it's going to have to contain that carbon on the CO bond. All right. Once we get that, we need to break that bond. All right, so this is the new bond that I'm creating. If I'm going to work backwards, I'm going to chop it. So let me actually take that over to this side here. Okay, I said that I created that new carbon-carbon bond, so if I'm going to work backwards, I'm just going to break it. And I got to identify which fragment is which. Right, so break bond. Identify which fragment is which. Meaning, which of these carbons belong to my Grignard and which of these carbons belong to my aldehyde or ketone. All right, and the key here is that this carbon with that oxygen bound to it, that's going to be my carbonyl carbon. That's going to contain that carbon-oxygen double bond. So that means that this fragment here, these three carbons, are going to be my aldehyde, and the other three are going to be my Grignard. So break bonds, identify which fragment is which. The fragment containing OH is the aldehyde / ketone. Could be either. Okay, so if I'm going to convert this into the aldehyde that it was, that means I'm going to get rid of this hydrogen and make this carbon-oxygen double bond there. Right, just to sort of show you what I did again. I'm going to take my alcohol, I'm going to get rid of this hydrogen. That should be a carbon-oxygen double bond. That's my aldehyde that I started with. Right, that means that these 1, 2, 3 carbons are my Grignard, so I'm going to have to just put that MgBr on there. All right, specifically the MgBr needs to go on the carbon that was attached to the other carbon. In this case, this molecule was symmetric, so I kind of could pick either side. All right, and then what your homework's actually going to ask you for is not the Grignard with the MgBr, but the alkyl halide that was used to create that Grignard, right? So instead of writing MgBr, you're just going to write Br. Those are the two fragments that it's looking for. Okay, let's do another one. Make it bigger and uglier. All right, so before we actually get started here, there are 3 possibilities for our new carbon-carbon bond. I want you to identify what those 3 possibilities are. Which one of these bonds, again there's 3 of them, could be the new carbon-carbon bond that I created in this reaction. All right, the only thing that I know for certain, again, it could be multiple possibilities, is that this carbon right here, the one at the base of that carbon-oxygen bond, that new bond is going to be with that carbon. So my three possibilities would be this one, or that one. Any one of those could be my new I could pick any one of those and get a set of Grignards to create that new carbon-carbon bond. Okay? So I'm gonna, for the sake of making sure we're all on the same page, I'm gonna arbitrarily say that we're gonna make it this one. You're gonna give me the reactants that I would need to create this as my new carbon-carbon bond. So again, all about working backwards. It is. So again, if I take my starting molecule, make that a CH3 so we can see what's going on here. I'm gonna work backwards. That means I have to break that bond that I just said was newly created in the reaction. So I'm gonna go in and break that bond there. One of these fragments is going to be my aldehyde or ketone. The other one is going to be my Grignard. All right, so I want you to take a second and determine which one should be the aldehyde or ketone, the one on the left or the one on the right?
The left.
The one on the left. Why the one on the left?
Because it has the oxygen.
Because it contains the oxygen, right? So that oxygen is going to be my carbonyl oxygen. So if I'm going to sort of redraw things just to keep it neat, I'm going to redraw my 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. And I'm going to put that carbonyl bond on carbon 4. So this would have been my ketone for this particular reaction. So if this is my ketone, that means that other side is going to be the Grignard, yeah. Okay? And again, there's sort of no logic between, I sort of arbitrarily picked this bond. You could have picked any one of those three and done this same sort of working backwards procedure. Unlike some of the reactions that we've learned about, there's no logic between what fragment has to be the Grignard and what has to be the aldehyde or ketone. You can just pick any of those bonds. What's your question?
Will there only be two reagents when talking about Grignard reactions?
So if we're being really good, there's always this second step that involves acid. We don't really need to know what it's doing. I'll tell you that this hydrogen actually comes from your acid. We're not going to be learning the reaction mechanism, which is when that would be a key player. But yes, if you see your list of reagents for a Grignard reaction, it's always listed as like the Grignard, MgBr, and then in a second step, following up with some source of acid. Okay.
There would never be like two groups of the MgBrs.
No, we are not going to do anything fancy that's going to require two different Grignards or anything like that. That was your question?
Yeah.
Yeah. All right, so again, make sure that we're really good at this. So I know that all y'all are super psyched to be learning these particular reactions because you're gonna go on in your careers and just do tons of Grignard reactions all the time. Like, no, okay? But truthfully, this is one of the most important synthetic reactions in organic chemistry. It is like the most basic, cheapest way of creating new carbon-carbon bonds. It is something that you would no doubt do in the lab when you're studying organic chemistry if you were like going on to be a chemist. So that's why it's kind of emphasized in multiple chapters here. And we're gonna spend some time making sure we're really good at it. Okay, we're gonna do one more here. All right, and y'all are gonna take it from the top. There would be two different possible answers. I'll show you both of them, but try to give me just one of them. That's all you need.
Do you want us to draw the Grignard or like do the formula for it?
The only reason that I did it here is because it's a methyl group, which is really small. So BRMG is what it would look like. It's just a little confusing. So typically with the methyl, you explicitly write CH3, but no, you can just do the bond line structure.
Okay.
All right, and what's that one way that we can sort of easily check if we've gotten it correct? Count carbons. All right, so everybody take a second, count your carbons. Make sure you got the same number of carbons on both sides of your reaction. All right, I'm gonna get rid of this just to make some room. So we're gonna need to do 2. All right, so looking at this molecule, there's one thing that I know for sure, which is my new carbon-carbon bond is going to involve this carbon right here, the carbon that's at the base of that oxygen. It can either be this one, so that's what I'll do on the top, or this one. Either one of those could be my new carbon-carbon bond. All right, I just know it has to involve that carbon at the base of the oxygen. So if you chose that one, you go over here. Again, we're going to break at that bond that we're saying is our new bond. We got to decide which fragment is which. And the fragment that contains the oxygen is my aldehyde or ketone. Right, so now I have this fragment here. I'm going to get rid of this hydrogen, create what in this case is an aldehyde. For my Grignard, I'm going to need to make sure that that magnesium is on the carbon at that other side of my new bond, right? I said that this bond here, this bond right here was the one that I'm creating, right? So that's going to be my carbonyl carbon in my aldehyde, and it's going to contain the magnesium. What's up? Okay. On the other side. So, take a second and do it on your own if you have not already. Again, now we're going to create this other side as our new carbon-carbon bond, which means that my magnesium is going to need to be bound to this carbon here, labeled in green. All right, that's my new carbon-carbon bond that I'm creating. So again, I'm going to split it at that bond. The side containing the oxygen is going to be the aldehyde or ketone. In this case, it's an aldehyde. So I'm going to convert that OH into a carbon-oxygen double bond. And the other side is going to be my Grignard. So that carbon that was involved in that new bond has to have the MgBr on there. Cool? Cool. All right, another important set of reactions for aldehydes are ketones. Talked a little bit about before, but let's make sure we're really good at it. Involves this thing here, which is lithium, aluminum, hydride. All right, these are almost always studied along with Grignards because they react. The mechanism in which they react is very similar. We're not going to worry too much about mechanism, okay? But again, we're going to be starting with an aldehyde or ketone. So let's just sort of arbitrarily pick one here. We'll be reacting it with our lithium, aluminum, hydride. It's also, if you see this list of reagents, it will have a second step where it's either water or some form of acid. Either one of them would work. Again, not really important for our purposes. The lithium aluminum hydride is the dead giveaway about what's going to happen. And similar to our Grignards, the functional group we're going to get on the other side is an alcohol. Okay? The difference is we're not creating any new carbon-carbon bonds. We're going to be creating new carbon-hydrogen bonds. So this product here, again, it converts that aldehyde or ketone to an alcohol. The new bond that you've created is, we don't even like explicitly draw it, but if I were going to be good about it, I would put a hydrogen is now bound to that, what was formerly the carbonyl carbon. That's the new bond that we're creating. All right? But honestly, we can make it even easier than that. Just turn your carbonyl group into an alcohol. That's just how you predict the products of these reactions. It's nothing fancy, nothing too difficult like with the Grignard where you get this big ugly thing on the other side. You're just going to turn that carbonyl bond into a carbon-oxygen single bond, into an alcohol. So if we had something like this, what would my product be? Everybody take a second. All right, so I guess again, we can be good and write our step-by-step procedure. It's much easier than with the Grignard, but nonetheless, first thing we're going to do is draw the carbons from my aldehyde or ketone. right? I'm gonna make sure I have the same 1, 2, 3, 4 carbons on my product side as I had on my reactant side. And then I'm just gonna convert that carbonyl into an alcohol. So this carbon here that used to have a carbonyl is going to now have an alcohol. Does anybody remember what type of reaction this is? The opposite of an oxidation reaction.
Reduction?
So this is a reduction reaction here, where you have less carbon-oxygen bonds. Importantly, just to make sure we remember, we actually know how to go the other way as well. And this was actually the first set of reactions that we learned, was converting alcohols to aldehydes or ketones. Let's take a second and see if you can't fill in. You'd be given a list of reagents on the exam, right? So if you don't have it memorized, it's not the end of the world, but you do need to be able to pick it out from this big long list of reagents here. Right, in this last unit, we've learned many more reactions than we've had up until this point. So getting them straight, keeping your reagents straight is going to be really important. Flashcard the crap out of them, right? That's what you want to do, is have each of these different reagents on a flashcard. You pull it out, you know what it does. That's the important thing. So, unlike reduction, which just always uses the lithium aluminum hydride, we have different sets of reagents that we need if we have a secondary alcohol. This requires one of those chromium-based ones, like, what the hell? Chromium 6 oxide or the sodium dichromate, right? When you see chromium, you think oxidation. For the primary alcohols, we have to use something a little bit more fancy, something a little bit more expensive, and that is PCC, and those are the two abbreviations, PCC or DMP. Either one of those would be equivalent. Those convert primary alcohols to aldehydes. Why can't I use those chromium-based ones? What's that going to do to a primary alcohol?
It's gonna make it an acid.
It's gonna still oxidize it, but it's gonna oxidize it all the way to a carboxylic acid. Whoa. Where it adds 3 carbon-oxygen, or I have 3 carbon-oxygen bonds in my fully oxidized product. Okay. Let's just practice these again. Some other reactions that we can review that we should know.
What happens if you do the lithium with the already alcohol?
It's pointed the other way. The arrow is telling you, is saying, what do you need to use that you're going to hit with the lithium aluminum to create that alcohol? It's not starting with the alcohol.
Oh, okay. I see that. Okay.
All right, so this is exactly what you can expect to see on the exam, one of these little webs here, okay? Because it's really just a compact way to force you to practice a bunch of different reactions. All right, starting out with this one alcohol, what's going to happen when I hit it with the sulfuric acid versus the potassium tribromide versus the chromium 6 oxide, et cetera, et cetera. So take a second and see if you can't review reactions that we've studied up until this point for this unit. All right, so again, these are great ways to practice the various reactions that we learned about. If you have a study partner, you guys can use this sort of format where, you know, one of them creates a little wheel and then the other person tries to solve it, okay? Also, if I was in your shoes at your age and somebody was like, yeah, grab a study partner, I'd be like, okay, yeah, right. I was very introverted. Wasn't gonna happen, all right? But nonetheless, just creating this thing, even by yourself, sort of knowing what the reactions are, can be really helpful. You don't need me to put this alcohol in the middle, right? You can just choose any old molecule, stick it in there, and see if you should know what happens to that functional group, right? Whether or not a reagent does anything to that particular functional group. All right, so let's start over here. So these were the ones that we were just talking about. What functional group is going to react with lithium aluminum hydride to give me an alcohol? That's an aldehyde, yeah. So in this particular case, it's an aldehyde, but yes, aldehydes or ketones would react with lithium aluminum hydride. And then if I'm trying to go the other direction, what would I have to use? PCC or DMP, either one of those, are weak oxidizing agents. Because of, right, so we called these guys weak. They only have 3-letter abbreviations, I don't know. Anyways, if we hit it with one of the strong ones, what's gonna happen? What is it? What am I gonna get functional group wise? Carboxylic acid. Notice that I have the same number of carbons. What the heck did PBr3 do? It does, yes. So we get what's called a substitution reaction. So yes, we swap out that OH group for a bromine. Right, again, kind of context clues here, that bromine in there. And then this one I feel like is one of the harder ones to remember for no good reason. Does anybody remember what functional group we get if we treat an alcohol with a strong acid? These are these elimination reactions. They create alkenes. So this carbon that was at the base of that oxygen, now it has a double bond, carbon-carbon double bond with its neighbor. All right, cool. So we're going to introduce another reaction to the whole mix, something called a Wittig. I think that's how you say it. Okay, these are going to use these reagents. Let's see. Where you have an R group, so you're going to be creating a new carbon-carbon bond. And it's double bonded to PPH3. All right, we don't really have to know what the PPH3 is, but I know that everybody is just dying with curiosity. This is actually a phosphorus that's attached to 3 different benzene rings. Okay, luckily that doesn't really play a role in this reaction here. The important part is what's going on this end here. Okay. If we have an aldehyde or ketone, this will react with our Wittig reagent. Okay? And what we're going to do is swap out this oxygen for this R group. Okay, so my product here is going to look like this. That oxygen gets completely replaced, and whatever's on the other side of the Wittig is now double bonded to the carbon that used to be a carbonyl carbon. All right, so let's look at a specific example. We can go ahead and stick with the same ketone. Does anybody remember the name of this ketone? It's got a special name. Acetone. So again, if we're going to sort of step by step here, we're going to just redraw our aldehyde or ketone, but we're going to erase that oxygen, right? That carbonyl oxygen. And then we're going to attach our Wittig at that double bond. So this carbon here used to be my carbonyl carbon, is now going to be double bonded to this carbon here on my Wittig. right? So we can convince ourselves that I indeed have the correct number of carbons. I'll color them even. So 1, 2, 3 from what was originally my ketone. Then I have 1, 2, 3, 4. 1, 2, 3, 4 from my Wittig reagent. What's up?
So on our homework, we're never gonna have to, we won't have to draw like the phosphorus and the
No.
benzene ring.
No, for this particular one, we're going to be worried about the forward direction, predicting products. All right, so let's just do another one. All right, so this is gonna look a little weird. You should have two rings attached together with a double bond. Because again, I'm gonna start by just redrawing that aldehyde or ketone, my six-membered ring. I'm gonna draw that carbonyl bond, but I'm gonna erase that oxygen. And now I'm going to attach my Wittig, what was formerly the carbonyl carbon, to what's at the base of that big ugly PPH3 deal. An upside down pentagon. All right. Bear with me. Close enough. So those ones aren't too bad. All right, we are making new carbon-carbon bonds, but for whatever reason, the attachment seems to be a little bit easier to comprehend than with our Grignards. The Grignards, I think, are probably the more difficult ones in terms of predicting products, just because you get a big, ugly molecule at the end of the day. Oops. Okay, so we've got a few minutes left. Again, let's just practice. lithium, aluminum hydride. What functional group do I get at the end? Alcohol. I convert my carbon-oxygen double bond to just a carbon-oxygen single bond, which again we called reduction reactions. When you see chromium, you think oxidation. All right, I guess I could have saved some space here because really it was just that exact same alcohol. All right, oxidation and reduction are opposite of one another. And then these two, we called this one a Wittig. It's got to be the dude's name. All right, Grignard. Both of these are going to create new carbon-carbon bonds. For the Wittig, we're going to draw our starting ketone, but without that carbonyl oxygen. And then we're going to attach what's on the other side of our Wittig to what was formerly that carbonyl carbon. So this would just have a methyl group there. You actually wouldn't even have to write it. You could just do it like that. All right, and then the Grignard, same sort of idea. We're making a new carbon-carbon bond. The carbon that I'm using is at the base of that magnesium, and it's going to be attached to that carbonyl carbon. So I'm going to draw my 4 carbons for my carbonyl. I'm going to make that what was formerly a ketone oxygen into an alcohol group. And then I'm going to attach the 1, 2, 3 carbons from my Grignard. All right. So these are the first set of reactions that we're going to learn. I'm going to warn you next time we're going to have another one that's going to be not so bad when you take it step by step, but you're going to look at, I'm going to put it up on the board and you're going to be like, what the heck is that? All right. So let me just impress upon you something that I've been reiterating throughout this unit is just that there are a lot more reactions than we've seen before, right? Keeping them straight is really important. And if that's something that you put off until the last night before the exam, that is a terrible strategy. All right, so just start trying to chip away at them now, and then when we learn a new one, it won't be like adding to this mountain of work that you have, right? Cool.